Okay, let's unpack this. The speed at which AI is advancing, tackling genuinely complex tasks, is pretty astounding.
It really is.
We're seeing models like, OpenAI's O1 and DeepSeek's R1 handle what looks a lot like real reasoning, planning even. So today we're diving deep into the nuts and bolts of these large reasoning models, or LRMs, based on some fascinating recent analysis.
That's right. We've got this compelling piece from the Annals of the New York Academy of Sciences, How Do Reasoning Models Reason? It offers, I think, a great high-level perspective on these new LRMs, highlighting their potential, the sort of core techniques behind them, and also tackling some of the common misunderstandings that are, floating around.
Exactly. We're not just taking the hype at face value here. We want to understand the fundamental mechanisms driving these breakthroughs.
Right.
When are these models truly effective? And, just as important, what are their current limitations? So our mission today is to really get under the hood, explore the two primary approaches being used to construct these reasoning models. And we definitely want to address some of the key questions, especially around this whole notion of AI reasoning. Is it really reasoning?
Well, what's fascinating is that the methods, they largely fall into two main camps.
Okay.
The first is what's known as test-time inference.
Test-time inference.
Yeah, think about it this way. When you face a really tough problem, you don't just jump to the first answer that pops into your head, right?
No, definitely not.
You probably pause, you consider different strategies, maybe double-check your work. Test-time inference tries to get LLMs to do something similar, basically, to put in more effort during the problem-solving process itself.
Okay. So it's about making the model work harder when it's trying to solve the problem, not just relying on its initial training.
Precisely.
Yeah.
One common strategy here is the generate test framework.
Generate test.
Exactly. The LLM doesn't just spit out one answer, it generates multiple potential solutions.
Okay. Like brainstorming.
Kind of, yeah.
Yeah.
And then, crucially, there needs to be some mechanism to select the best one out of that batch.
Right. So brainstorm first, then judge.
That's the idea. You need a system to figure out which generated solution is most likely correct.
And I guess one of the simplest ways is that self-consistency thing, where you just pick the answer that shows up most often.
That's one way, yeah. It's straightforward. The hope is, even if some attempts have errors, the correct answer might emerge as the most frequent one.
But no guarantees, right?
No, absolutely no guarantees. It's heuristic. The most common answer isn't necessarily the right answer.
Okay, so it's like polling the model's own guesses. A bit basic, maybe. What are the more sophisticated ways to pick the best solution?
Right, so this is where the test part gets more refined. Researchers are exploring various verification methods.
Like what?
Well, you could use another LLM as a verifier. Although, LLMs aren't perfect judges themselves, are they?
True. Fallible verifiers.
Exactly. So there are also efforts to train dedicated learned verifiers. Or, and this is interesting, use external sound verifiers, systems that can definitively confirm correctness.
Like formal methods, mathematical proofs.
Kind of, yeah. Our own LLM modulo framework, which the paper mentions, aims for that sort of guarantee through formal verification, like a checkable proof.
Got it. That makes sense, having an objective way to say, yep, this one's definitely right. The paper also mentions feedback loops, where if a guess is wrong, that info helps guide the next try.
Exactly. It's an iterative process, much like how we might adjust our approach if we realize we're going down the wrong path.
Yeah.
This whole area, test-time inference, it really does mirror how we tackle complex problems, thinking longer, trying different things.
Okay, so that's one major piece. Getting the LLM to exert more effort during problem solving. What's the other main approach?
The second big strategy focuses on what happens before the model even sees a problem. It's about post-training on what the paper calls derivational traces.
Derivational traces, okay.
So let's quickly remember how standard LLMs are trained. You know this, they're fundamentally about predicting the next token, right? Learning patterns in text.
Right, statistical pattern matching on a massive scale.
But the core idea here is that the initial training data, all that text, might be missing something crucial.
Which is?
The reasoning traces, the intermediate steps, the how you got there part of solving a problem.
The working out, like in a math problem.
Exactly. The final answer is one thing, but the sequence of calculations, the logic, that's the trace. The hope is, if you explicitly train LLMs on these steps, they'll learn to replicate similar processes.
That sounds logical, but where do you get that data? I mean, the internet isn't exactly full of detailed step-by-step thought records for everything, is it?
That's a huge challenge. The paper really highlights this. It's hard for us humans to articulate every single step of our reasoning.
Yeah, sometimes you just, or can't explain it easily.
Right. And we might not even be consciously aware of all the little cognitive jumps. There's that great anecdote in the paper about Goss. Someone asked him about his proof intuitions, and he apparently quipped that a self-respecting architect doesn't leave the scaffolding up after the building is complete.
Oh, nice. So the how often just vanishes.
Pretty much. The evidence gets effaced. So getting that data is tricky.
Okay, so how are researchers trying to get around this scarcity? What are the techniques?
Well, several approaches. One is just direct human annotation.
Paying people to write out the steps?
Essentially, yeah.
Yeah.
Like with the GSM-AK math dataset. People
Yeah.
created detailed step-by-step solutions. It works, it's effective, but...
Super expensive, doesn't scale well.
Exactly.
But-
Very resource intensive. Another way is using formal solvers.
Like automated planning tools?
Things like Search Former, Stream of Search. These can automatically generate solutions and the detailed execution traces. But
I only work for specific domains where you have those solvers, right?
Precisely. Limited applicability, not a universal fix.
Okay, so human annotation is costly. Formal solvers are domain-specific. What about the third way? Didn't the paper mention using LLMs themselves to generate traces?
Yes, exactly. That's a really interesting angle.
Yeah.
The thinking is, LLMs have already seen tons of text, right? And some of that includes explanations, examples of reasoning, show your work type stuff. So you can try to prompt them to generate these intermediate steps themselves. Even something as simple as adding "let's think step by step" to the prompt.
That actually works, just telling it to think step by step.
It often encourages that kind of output, yeah. And it's quite remarkable, isn't it? Shows the model's ability to pick up on and mimic patterns associated with problem solving.
Wow, that's clever. But I imagine those generated traces, they can't always be right or even helpful.
You're absolutely right. They won't be perfect, and that's where filtering comes in.
Okay, so you generate potential traces, then you sift through them.
Exactly. You need to evaluate and select the good ones. This can be done in a few ways. You can have human reviewers check the logic of each step.
Again, expensive.
Yep. Or you could train reward models to automate that assessment. Or sometimes the filtering just focuses on whether the trace leads to the correct final answer.
Ah, so you don't necessarily care if every intermediate step is perfect as long as the end result is right.
That can be one approach, yes.
Yeah.
Verify the final solution and keep the trace that led to it.
Okay, so once you have these filtered, hopefully useful derivational traces, how do they actually improve the LLM? What's the mechanism?
Well, early approaches just involve direct fine-tuning. Feed these good trace examples back into the LLM training.
Makes sense. Show it more good examples.
But more recent and arguably more successful methods have leaned towards reinforcement learning, RL.
Ah, RL, like in game playing AI.
Similar principles, yeah. DeepSeek's R1 models are a key example here.
Yeah.
After pre-training, they go through an RL phase.
How does that work in this context?
They're given questions, typically ones with automatically verifiable answers, like math problems. For each question, the LLM generates multiple completions, including the intermediate steps, the trace, and the final answer.
Oh.
Then these completions are scored, usually based simply on whether the final answer is correct.
Right.
And the model gets rewarded for the completions that led to the right answer. This makes it more likely to produce similar outputs, similar thought processes in the future.
So it's learning by trial and error, essentially, trying different ways to solve it and getting positive feedback for success.
That's a good way to put it.
Yeah.
And the paper notes, conceptually, this RL process isn't that different from standard fine-tuning in this context. It's basically a cycle. Generate, check the answer, selectively reinforce based on correctness.
Interesting.
Yeah, and there's also this observation that you can sometimes train a model with RL, get its verified outputs, the good traces and answers, and then just fine-tune a second LLM on that curated data.
That's distillation.
Exactly, distillation. And now there are even public data sets of these filtered traces, like open thoughts. So you could potentially bypass the whole complex RL phase.
Like learning from the teacher's perfect solutions instead of watching them figure it out.
Precisely.
Okay, so we've got the two main strategies down. Test time inference, more effort during solving and post-training on these derivational traces, learning from step-by-step examples. Now, the big question, How well do these LRMs actually work? How good are they?
Ah, yes, the performance question.
Yeah.
This is where things get really interesting and maybe a bit complicated.
I bet.
The excitement is definitely there, fueled by improved scores on reasoning benchmarks. Companies like OpenAI, DeepSeek, they heavily promote these gains.
We see the headlines.
Exactly. And, our own independent analysis using PlanBench, that's a set of relatively simple planning problems, it did confirm improvements. These newer models solve problems that older ones just couldn't handle.
So there is genuine progress then. That's encouraging. But the paper also flags limitations, right?
Oh, absolutely. While they're an advancement, they still suffer from generalization failures. Meaning, they might do well on the specific types of problems they were trained or benchmarked on, but struggle when things change slightly or get bigger. They still have trouble with larger instances of even quite straightforward problems.
Okay. And what about when a problem can't be solved?
That's another major issue. They show significant hallucination on unsolvable problems. They don't just fail gracefully and say, I can't solve this.
What do?
They often confidently generate impossible plans or solutions and then try to justify them with elaborate but completely false reasoning.
Wow. That's concerning. That sounds quite brittle.
It is. It really suggests that while they might be better at guessing correct answers within known patterns, their fundamental understanding of constraints or even solvability itself hasn't necessarily improved in the same way.
So perhaps we shouldn't think of them as fundamentally different kinds of reasoners yet, but more as, what did the paper say?
The better generators with a higher density of correct solution guesses.
Right. That sums it up well.
And our own work with O1, using it inside the LLM modulo framework, showed that if you add that external formal verification layer,
the guaranteed check.
Exactly. You can further boost accuracy and, crucially, ensure you only get solutions that are provably correct.
Which makes that verification part seem even more vital, maybe not just an add-on. Now, shifting gears a bit, practicality. Are these LRMs cost-effective?
Ah, the cost question. That's a big one. Compared to standard LLMs, LRMs generally involve higher costs.
Both in training and using them?
Both. The training, especially with RL, or extensive trace generation and filtering, can be more complex and expensive. And then at inference time, when you're actually using the model,
it costs more per query.
Potentially, yes. OpenAI, for instance, apparently started charging for the intermediate tokens O1 generates during its thinking process, even if the user doesn't see them.
Really? You pay for the thought process?
Seems like it. And with test-time inference methods that explore many possibilities, the compute cost per query can become substantial, maybe even scaling with how hard the problem is.
That's a massive shift from the usual LLM model, isn't it? Where the inference cost is relatively fixed per token.
It's a huge shift for the business model.
Yeah.
LLM companies can't just rely on amortizing the upfront training cost anymore if the usage cost varies wildly.
So you really have to weigh the performance gain against potentially much higher operational costs. Makes you wonder if specialized systems might still be better for certain tasks, cost-wise.
It's definitely a trade-off to consider. Which leads to another fundamental question. How different are these LRMs from what we usually just call LLMs?
Yeah, is it just a souped-up LLM or something truly new?
Well, we know what LLM typically means. Transformer architecture, massive pre-training, often some fine-tuning like RLHF. LRMs are built on that same foundation, so are the changes big enough for a whole new category?
The paper points out that test-time inference does change the user experience.
It really does. A standard LLM usually streams its output, token by token. You see the answer forming? Systems using complex test-time inference, especially exploring multiple paths, might lose that. You could be waiting quite a while, then get the whole answer at once. No streaming.
That's a pretty noticeable difference. But what about the ones mainly post-trained on traces, like DeepSeek's R1? Do they behave differently at inference?
The paper argues, perhaps controversially, that at inference time, they still function like standard LLMs. They take a prompt, they generate a completion.
But the completion looks different, right, with all the intermediate steps?
Exactly. The type of completion they're trained to produce is different. R1 is trained to output those intermediate reasoning tokens before the final answer. But, and this is the key point at the underlying execution level, it's just generating tokens sequentially, same as any LLM. Those intermediate tokens don't have some special operational meaning to the model itself.
They just look like reasoning to us.
Precisely. They're just part of the generated sequence the model learned produces good results according to its training objective.
So the idea that having variable length intermediate thinking is some new test time scaling paradigm, the paper pushes back on that.
It does. The authors contend that LLMs have always produced variable length outputs, and you could often get scratchpad or a chain of thought style outputs from older models with the right prompting.
Yeah.
It's not fundamentally new in that sense.
Okay. And the paper brings up that old argument about LLMs being approximate retrieval systems again.
That they're mainly recalling and recombining patterns seen during pre-training. The crucial question then becomes, are LLMs genuinely moving beyond that? Are they becoming independent enough from the pre-training data to do novel reasoning?
And is there evidence either way?
Well, there's some evidence suggesting performance on benchmarks might still be tied to whether similar problems were in the pre-training data. So the jury's still out on whether they fully escaped that retrieval loop.
Which brings us smack into the middle of probably the biggest question. Are these things actually reasoning, or are they just getting incredibly good at retrieving or generating sequences that look like reasoning?
This is the core debate, isn't it? And it's a really important distinction to try and make.
Yeah.
The paper points out, look, most of the big advances we're seeing with LRMs are on tasks where you have a formal verifier. Math problems, coding, simple planning.
Things where you can definitively check if the answer is right or wrong.
Exactly. And the current successful strategy seems to be leveraging those verifiers, using them in a generate test loop, maybe at test time, maybe during training via RL, maybe during distillation.
So you're essentially using the verifier signal to teach the generator how to produce correct answers more often.
That's the argument, that post-training LRMs are, in effect, iteratively compiling reasoning into retrieval.
Compiling reasoning into retrieval. I like that framing.
It captures the idea that you're taking the logic, the verification step, and baking it into the model's generative patterns.
And you need iteration because models trained on small problems don't automatically generalize to bigger ones, right?
Right. The LLM trained on simpler stuff often struggles with larger instances. So you need this iterative refinement guided by the verifier. And of course, this whole process relies on the base LLM being good enough to propose something plausible in the first place.
The verifier needs something decent to work with. The top accuracy has to be reasonable.
Exactly. It connects back to Minsky's idea about intelligence, shifting the test part into the generate part. LRM post-training seems like a way to use the verifier signal, the test, to refine the base LLM, the generator.
And even DeepSeek R1, which doesn't use test time verification itself.
It still uses verifiers heavily in creating the synthetic data used to train other models via distillation. The verifier signal is still crucial, just applied at a different stage.
So this staged verification, training, test, distillation, it's all about embedding that correctness signal deeper, allowing the model to handle longer chains of reasoning, longer inference horizons.
That seems to be the current understanding. And the paper connects this view to lots of other findings, why chain of thought prompting works, differences between internal and external planning in games, even this idea of self-improvement in transformers.
Suggesting that self-improvement isn't magic, but maybe just the model getting better at internalizing that verifier signal.
That's the interpretation offered, yes. Compiling the verifier.
Okay, this leads us right to those intermediate tokens, the thinking steps. The paper raises a really provocative point here, doesn't it? Are they actually traces of LLM reasoning like human thoughts are?
Yeah, this is probably the most contentious issue and the one where the paper is most critical, I'd say.
Why is that?
Because there's such a strong natural tendency for us to look at those outputs. You know, let's break this down. Okay, the step-by-step stuff. And assume the model is thinking like we do. Anthropomorphism is hard to resist.
We see something that looks like our scratch pad and assume it's doing the same job.
Exactly. But the paper argues really strongly, just because it looks like human reasoning doesn't mean it is serving the same function inside the model, or that it gives us a reliable window into the LLM's actual process.
Because LLMs are just amazing mimics, right?
They're incredible mimics. They can imitate countless styles, so why not the style of someone thinking aloud? The paper even jokingly calls them large, mumbling models.
Okay. And practically speaking, verifying those traces is hard.
Incredibly hard.
Yeah.
Think about DeepSeek R1 generating pages of intermediate text for a relatively simple problem. Who's going to check if all of that constitutes valid, sound reasoning? It's often infeasible.
So most evaluations just check the final answer.
Pretty much. It's the only practical way right now. And we also need to distinguish between the raw intermediate tokens, the derivational traces, and the cleaned up post hoc explanations some systems generate after finding the answer.
Like rationalizations. We humans do that too, invent reasons after the fact.
Precisely. And those after the fact stories don't always reflect the actual thinking process.
And didn't the paper mention experiments where even models trained to follow specific algorithms produced steps that were wrong according to the algorithm but still got the right final answer?
Yes, that's a crucial finding. Even when format constrained and trained on solver traces, a significant fraction of the generated intermediate steps were invalid by the original algorithm's rules, yet they sometimes still stumbled into the correct final answer.
That really throws cold water on the idea that the correctness of the trace itself is the most important thing, doesn't it?
It seriously challenges that assumption. Yet so much research seems focused on making the traces perfectly correct and human-like.
Which the paper suggests might even be dangerous.
Potentially misleading, yes. If we deliberately make the traces look superhuman-like and logical, we might exploit our own cognitive biases, making us trust the output, even a wrong final answer, more than we should, creating false confidence.
So focusing on human legibility might actually be counterproductive.
It could be. Maybe what works best for the model isn't something that looks like human thought at all.
So what's the alternative perspective the paper suggests?
It proposes de-anthropomorphizing these intermediate tokens. Stop thinking of them as thoughts. Instead, view them as a kind of prompt augmentation.
Prompt augmentation, like extra input to help the main task.
Sort of. The idea is that all these methods, chain of thought prompting, fine-tuning on traces, RL, they're ultimately just ways of discovering the right additional input, the intermediate tokens, that helps the LLM produce a better final completion.
Okay.
And if you think of it that way, it opens up new possibilities. Maybe you could have another LLM whose job is just to propose and refine these augmentations. And maybe those augmentations don't need to use human words at all. They could be any sequence of tokens from the vocabulary that proves effective.
Like an internal language optimized for performance, not human readability.
Exactly. It even connects to adversarial attacks, which are also about finding weird inputs that trigger specific outputs. The paper suggests maybe using powerful RL methods, like from AlphaZero or MuZero, to learn an intermediate token language purely focused on maximizing final answer accuracy.
Regardless of whether it looks like thinking to us.
Precisely. Which, they note, was an early speculation about how OpenAI's O1 might actually be working internally.
Wow. That's a radically different way to think about it. Shifting focus from mimicking thought to optimizing performance via these internal augmentations.
It is. It moves away from trying to replicate human cognition towards finding what actually makes the system work better.
Okay, so let's try and wrap this up. To recap, we've looked at the two main ways these LRMs are built. Test time inference, making the model work harder at solve time, and post-training on derivational traces, learning from step-by-step examples.
That's the core distinction in methods.
And the key takeaway seems to be, yes, impressive progress on benchmarks, definitely, but still significant issues with robustness, generalization, hallucination.
Absolutely. The progress is real, but the limitations are just as real.
And the paper strongly suggests that maybe their best use case right now is as sort of supercharged generators, but ideally within a system that has some kind of external verification to guarantee correctness. Don't just trust the output blindly.
That seems like a very prudent conclusion based on the evidence. The verifier component is critical.
And we really need to be careful about interpreting those intermediate tokens as human-like reasoning, right? They look the part, but they might be doing something quite different functionally.
Yeah, that critical perspective, avoiding easy anthropomorphism, seems really important going forward. Their resemblance to our thoughts doesn't mean they're thoughts in the same sense.
Okay, so here's a final thought maybe for you, the listener, to chew on. If these intermediate steps, these traces, aren't necessarily reasoning in the way we understand it, what is the actual mechanism that lets these models solve harder problems than before? And if we could understand that mechanism better, maybe this idea of prompt augmentation or internal optimization, could that lead us to truly robust, reliable AI, perhaps faster than trying to make AI perfectly mimic human thought processes? What if the key really does lie in focusing relentlessly on that output verification, ensuring correctness, no matter how alien the internal process looks?